A very warm welcome back, innovators. I am absolutely thrilled to have you here with us for today's explainer. As always, we're joined by our lead expert, innovation catalyst, and educator, the Idea Mechanics Navigator. Notice him right over there in his signature red shirt, glasses, and that sharp silver accented hair. He is here to help us bridge that critical gap between abstract ideas and practical, on-the-ground execution using TRIZ. Today, we are completely transforming how manufacturing leaders approach mechanical force. We're going to be exploring the architecture of high-speed fluid power and thermal protection. Let's dive right in.
But right before we get into the heavy lifting, we need you on board. If you're ready to stop relying on luck and start mastering systematic discovery, hit that subscribe button to join the Idea Mechanics team.
And definitely don't forget to ring the notification bell so you're the very first to see our next innovation breakdown. We want to build this culture with you, so drop a comment below and tell us which TRIZ principle or tech challenge should we tackle next. Let's do this together.
All right, look over at the navigator as he points out our core definition on the screen. This is absolutely crucial, guys. We've got to shift away from that reactive trial and error mindset. Far too often, we treat innovation like it's this random lightning strike eureka moment, right? Like you just have to get lucky. But the navigator is here to show us that true innovation, what we call TRIZ systematic discovery, is actually a highly repeatable architectural discipline. It's a structured formula that directly solves everyday contradictions in your field. Basically, we're moving away from guessing and stepping into actual engineering. To really grasp the power of this systematic approach, let's take a look at the mechanical friction trap that totally bogs down traditional factories. The old way? Well, it relies heavily on slow processing and these incredibly complex mechanical linkages. What happens? You get excessive friction, severe wear and tear, and eventually material deformation. It's a constant, headache-inducing struggle that honestly keeps maintenance teams up at night. The systematic way, on the other hand, bypasses this friction entirely. It leverages high-speed execution to provide thermal protection and uses fluid dynamics to deliver clean, massive force. The best teams in the world don't fight friction, they literally architect their way around it. And that brilliantly brings us to our first major concept today, TRIZ Principle 21, also known as skipping or rushing through. Now, normally we're all told that rushing leads to mistakes, right? Haste makes waste? But in the world of physics and material science, rushing through a hazardous zone is actually a protective measure. By accelerating a process to an ultra-high speed, harmful factors like heat propagation simply don't have the time to manifest. Think of it like running barefoot across a bed of hot coals. If you walk, you burn. If you sprint, you're safe. Speed is your literal thermal shield. Let's watch the navigator break this down with a real-world case study, high-speed plastic cutting. Step 1, we identify the contradiction. When you cut plastics, the friction from the tool naturally generates heat. If you cut slowly, that heat spreads, the plastic melts, warps, and boom, your product is ruined. So, step 2, we deploy Principle 21. We bring in ultra-high-speed cutting tools to literally skip the thermal window. The tool moves through the material so incredibly fast that the heat generated just doesn't have time to spread. And step 3, the result is pristine, highly accurate cuts with absolutely zero thermal damage. The crucial takeaway here is that moving fast isn't a compromise on quality. It's the exact mechanism that saves your materials. Okay, now let's see how this builds into our second breakthrough concept, TRIZ Principle 29, Pneumatics and Hydraulics. While Principle 21 solves thermal contradictions using speed, Principle 29 solves mechanical wear and tear by substituting rigid gears with what we like to call fluid muscle. This principle is all about replacing physical mechanical systems with compressed gas or liquid pressure. Why would we do that? Because fluids transmit force so much more efficiently. They give you massive power, remarkably smooth motion, and extreme precision, all while taking up way less physical space. It's a total game changer. Notice how clearly the victory of fluid muscle over rigid mechanics is laid out for us here? Follow the navigator's cue and look at the winning column. Take force density, for example. Mechanical linkages are usually super bulky, whereas pneumatic actuators deliver immense force in a highly compact little package. Then look at wear and tear. Mechanical gears mean high friction and constant maintenance downtime, but pneumatics? Extremely low friction. And finally, cleanliness. Gears require messy, sticky lubricants, while pneumatic systems just use clean, compressed air. This essentially makes compressed air the ultimate cheat code for fast, clean, and incredibly reliable assembly line automation. So let's bring it all together, innovators. What are our core takeaways as innovation catalysts today? First, we absolutely must stop accepting deformed materials and worn-out gears as just part of the job. Second, we need to bypass hazardous thermal zones by using extreme speed as a shield. That is Principle 21 in action. Third, we systematically replace complex, failure-prone mechanical linkages with the clean, compact power of compressed air, which is Principle 29. And above all else, we need to treat factory breakthroughs not as strokes of luck, but as a deliberate architectural skill. These massive efficiency gains, they're an engineered choice, and it's a choice you have the power to make. We'll leave you with this final, provocative challenge from the Navigator. If innovation is indeed a repeatable formula, and not just some random eureka spark, where are you going to apply the architecture of high-speed fluid dynamics in your workflow tomorrow? Seriously, think about the friction in your current processes and how you can systematically architect it right out of existence. Thank you so much for joining us for this explainer. Stay curious, keep building, and we will catch you on the next deep dive.